background and motivation and context for the talk, I'm going to be going through the pieces of the title, mind your way, the title of the thesis, starting with the word asteroid. Why do we study the asteroids? Well, one of the overarching goals in planetary science is to study the formation and evolution of the solar system. And since there are only a handful of planets and that number is decreasing rapidly, it's sometimes hard to use the planets because of their small numbers. But there are 678,789 known minor planets as of today, and that number is just going up. So we really have a large sample size of planetary objects to study. Now the planets are also relatively processed. They've undergone their own thermal evolution, their own history to them, but the asteroids are often comparatively unprocessed. They're primitive remnants of our solar system that we can study. And sometimes they deliver pieces of themselves to our front door so we can make connections and sort of physically test our models for solar system formation and evolution through meteorites. So we want to make connections between meteorites and asteroids. We also want to explore the solar system, and asteroids are an excellent low delta V, if you know the lingo, platform for exploring the outer solar system using resources that exist already out in space to explore further. And then lastly, they present a security risk, so we do want to avoid mass extinction, so we want to study them and learn about them. So where are they? Here's a top-down view of the solar system. The inner planets are all here, out to Mars. Jupiter is this orbit here. And the asteroids primarily exist in this large green main belt. There are some asteroids that come particularly close. They are represented by the red dots here, near-Earth asteroids. So this plot is very congested. That's partly because all those dots are way bigger, not to scale, way bigger than the actual asteroids in the plot. But it also doesn't show us some of the structure of the asteroid belt. It's not just one big blob, it's structured. So if you look at how far each asteroid is from the sun, you can make a plot that looks like this. So this is a plot of distance from the sun, semi-major axis we'll talk about on the next slide. And the sun, Earth, and Mars are this way, Jupiter is off this way. This is the asteroid main belt, a histogram of the number of asteroids in each distance from the sun. And you can see right away that they're not evenly distributed throughout this space. There are gaps where there aren't any asteroids. These gaps are known as mean motion resonances. In particular, the ones drawn, the lines here, are with asteroid Jupiter. We'll talk more about what mean motion resonances are, but basically I want you to see from this plot that you can really get a sense of the dynamics of what's happening in the solar system, the history of the solar system, and through the asteroids' interactions with planets, which sculpts their distribution, as seen here. So if we want to talk about asteroids and their distributions, we need to talk about asteroid orbits. Asteroid orbits are ellipses, so you can describe their orbits with different sort of properties of ellipses. The first one, which we briefly talked about on the previous slide, was semi-major axis, or designated by A. And that's half of the long axis of the ellipse. So it's kind of like distance from the sun. And the eccentricity of the ellipse goes from 0, which is circular, goes toward 1, which is a lot more squished. So you can describe asteroids by eccentricity E. And then inclination angle is the tilt of the orbit with respect to a reference plane. And then omega and big omega are a little bit harder to picture and explain, but they're angles that describe the orientation of the orbit to the reference plane and direction. So in addition to asteroid orbits, we can talk about asteroid physical properties. You may think that asteroids come in about 50 shades of gray, but they're actually multicolored. Tiny variations in their color can distinguish one from the next. And that's really important because they tell us what they're made out of. And the Sloan Digital Sky Survey, SDSS, measured asteroids in 5 color filters and came up with these 2 parameters, A star and I minus Z, which are ways of describing asteroid colors. And then asteroid brightness and size. If you look at an asteroid in the sky, you'll see it looks to be a certain brightness. And we call that H. H is the brightness of the asteroid at a particular distance and angle from the Earth and Sun. That's absolute magnitude. But that brightness depends on the actual reflectivity of the surface. If you have an asteroid made out of asphalt, it's going to look different from an asteroid made out of beach sand, for example. And that property is called the albedo. It goes from 0, which is dark, to 1, which is bright. And then lastly, if you have a really big asteroid, it's going to reflect a lot more surface area, a lot more light from its surface area than a small asteroid. So Ceres is going to look a lot brighter than tiny Itokawa. So all three of these parameters are connected. If you have two of them, you can find the third. But now, there are some properties of asteroids that are very important, but a lot more difficult to actually measure. That's density or mass, and then shape and spin and composition. So now, if we combine orbital information with color information, we can learn a lot about the structure of the asteroid belt. So again, here is semi-major axis, and you see the familiar resonance gaps in the distribution here. And if we plot the semi-major axis versus the inclination, another orbital parameter, we end up seeing that they're not uniformly distributed in orbital space. These objects all kind of clump together. And those clumps are very important. As you can see from the color scheme of this plot, which is designed to represent those Sloan Digital Sky Survey colors I mentioned, the clumps each kind of have a distinct color. And that leads us to talking about asteroid families. Drink? So asteroid families, over the past century, scientists have begun to realize that those clumps are not just random. They're probably groups of asteroids of a common origin, most likely collision fragments. And even more recently, we've begun to discover that these are sources of near-Earth objects. Near-Earth objects, like I said, they provide those asteroid-meteorite connections. So the asteroid families really provide an important context for our study of the solar system. You can get the ages of asteroid families, and that helps you find out the chronology of the asteroid belt and the history of the solar system. And then family characteristics can help you test models of solar system formation and evolution, as well as make meteorite asteroid connections. So in order to study asteroid families, you need to first identify them. As you can see, a lot of them are overlapping in the orbital parameter space. So we need to identify what's really in the family in order to study it. And the traditional method for doing this is called the hierarchical clustering method. And I've got a little cartoon here, which I'll use to try to explain how this method works. Whoops, spoiled my next slide. So you start with a group of asteroids here, and you measure all of their distances in the orbital parameter space, distances from each other. And you notice that all of these are clumped together, and these are not clumped together. And you say, okay, well, the top, maybe they're two separate families. But, here's the punchline. What if you have an object that is right between those two? It could possibly create a bridge between the two families, and you might dynamically connect them and say they're actually one family. So that presents a problem for this method. You might be able to look at the color information. Notice these are maybe more blue, and these are a little bit more red, and that might help you distinguish families from each other. But in general, this chaining, as it's called, creates a problem for this method, especially in regions of a lot of overlap, like the inner main belt here. So I developed, with my collaborators, a method called the core sample method for family identification. And we'll go through a little bit of an example of how that works. With the Vesta family, this green blob here represents the asteroids of the Vesta family, and the big red diamond is Vesta itself, the parent of the family. So the core sample method recognizes that you've got interlopers, non-family members, strewn all throughout this family. But the place where they're likely to be the least dense, where the family members are likely to be the most dense, is the core. So if we take a sample from the core of the family, we can ask what are the colors of the objects in that core. And after we ask that question, okay, what are these colors? Then we figure out these are the colors of a typical Vesta family member. And then we can plot the distribution in the orbital space of all of the objects that have that typical color. And we can start to learn about the, say, the Vesta family's extension in semi-major axis and inclination in this plot. So that's an overview of the core sample method. So we talked about asteroid families. Now, asteroid families do not stay the same. They change, so we can talk about asteroid family dynamics. One of the reasons that asteroid families change is because of gravitational interactions with the planets. We talked earlier about these mean motion resonances. These are places where the asteroid's orbit is an integer ratio of the orbit of a particular planet, in this case Jupiter. So for example, this is the 3-to-1 mean motion resonance with Jupiter. That means as the asteroid goes around 3 times, Jupiter's gone around once. And they end up in the same place every time. And you know, normally when you're going through your orbit, you're a happy asteroid going through your orbit, and you see Jupiter a bunch of different ways. It tugs on you in a bunch of different ways. And your orbit doesn't change much because those are sort of chaotic interactions. But in these places, you actually can build up changes in the asteroid's orbit, and you can get evicted from the asteroid belt. And that's very important because if we are going to get asteroids that are going to impact the planets, we need ways to get them out of the asteroid belt. And these resonances are ways to get them out. But, okay, so for our family, the Vesta family here we were just talking about, you can see that some of the objects of the Vesta family are very close to the 3-to-1 resonance with Jupiter. So likely, pieces of Vesta have gotten into that resonance and come and hit the Earth. And we see evidence for that. These are howardite, eucrite, and diogenite meteorites, which actually look a lot like Vesta, so look a lot like Vesta family members. So we think that they came from asteroid Vesta. But now you might think, well, okay, so some of these guys are in trouble. They're going to head our way. But most of these asteroids here are safe. They're not going to actually interact with the Earth. But there's another force at play, and that is the Yarkovsky effect. It is not a gravitational force. It is a force of the tiny force of sunlight acting on the surface of asteroids. And actually, I've said this a whole lot better in the movie that I created with the OSIRIS-REx 3-to-1 science team describing the Yarkovsky effect. So we're going to watch a minute of that movie. And just because this is a Russian word and it might need a little help with the pronunciation.
Can you say Yarkovsky? Can you say Yarkovsky? Can you say Yarkovsky? Yarkovsky?
Okay, so he's getting better. He's getting better at it as the days go by.
Just like the Earth, asteroids are spinning as they orbit the Sun, so they have a day and night cycle too. Because of this rotation, the warmest part of an asteroid isn't the spot right in line with the Sun, it's slightly to the side. As the photons radiate from this warm spot, they give the asteroid a little kick, similar to the recoil force on a firing cannon. This recoil force can slow an asteroid down, or speed it up, like a car when the driver pushes the gas or brake pedals. If the asteroid is spinning such that the warmest spot is slightly in front, the recoil force will be backwards, and the asteroid will slow down a bit, like a car hitting the brakes. But if the asteroid is spinning the other way, the warmest spot will be slightly behind, and the recoil force will give the asteroid a push forward in its orbit, like a car hitting the gas. These tiny forces can change the asteroid's orbit. If the asteroid speeds up, the orbit will expand. If it slows down, the orbit will shrink. The Yarkovsky effect is...
All right. Okay, I gave myself a break there. Now that we all have that song stuck in our heads, we can continue. So the important thing to realize from the video, the punchline, is that asteroids are going to drift in semi-major axis in distance from the Sun, and they're going to drift in a different way based on their spins. If they're spinning what we call prograde, they're going to spin outward. If they're spinning the other way, retrograde, they're going to spin in, or they're going to spiral inward. And these these are a bit extreme. It actually takes millions of years, and it's a very small effect. So the Yarkovsky effect, coupled with these resonances, these escape hatches, provides an efficient dynamical pathway for making near-Earth objects. So we really want to study families in order to understand how these effects work and use these effects to study families. Another important detail about the Yarkovsky effect is that it is size-dependent. So here I'm going to try to explain what we call the V-plot, which you'll see a lot in this talk. This is a distribution, a make-believe cartoon distribution of a collision right after it happens. You've got size distribution, a big object here all the way up to the smallest objects, and they're all generally at the same semi-major axis. But over time, they're going to spread out from the Yarkovsky effect. So after a while, the smaller objects have traveled further than the largest object, and that's because they have a higher surface area to volume ratio. And then after quite a bit of time, as the family ages, they get even more spread out. This is the theoretical framework for how this works, but we see it observationally too. Here's an example of the Massalia family. This is object 20 Massalia in the same semi-major axis versus size or absolute magnitude. And we can see that the family is quite dispersed. And we can use that amount of dispersion to try to measure the family's age. And the way that we do that is to quantify the amount of dispersion using this C parameter. The C parameter describes how much dispersion has happened for a given size, and here's the relationship between the three. And the more dispersed you have, the higher C parameter will describe the boundary of the family. So that was asteroid family dynamics in a nutshell. Now we'll look at the inner main belt and ask how we can apply these techniques to the inner main belt. So in particular, my dissertation studies the low inclination inner main belt, which is indicated by this white box here. So we've seen this plot already, but I want to point out that a lot of these families are very old, so they're very dispersed, very spread out horizontally in semi-major axis. So it's often helpful to look at other orbital parameters, such as eccentricity versus inclination, to study these families. You can see the Vesta family here is much less dispersed in eccentricity. So why do we study the inner main belt? Well, frankly, it's a big source of near-Earth objects, but it's a really challenging region to study. So it's hard to get the characteristics of the family because there's just a lot of families there, and they're all overlapping. So I will quickly take you on a walk through the inner main belt neighborhood and meet some of the families. We talked about the Vesta family already, but there's also the Baptistina family, this purplish dot here, the Nysa complex, which is actually 4 families overlapping. And then we talked briefly about Massalia, which is here. And we'll be talking about the Flora family, which is spread throughout the entire inner main belt. It's actually a really difficult family to study because it's very diffuse, it's very old, and some have argued there might be a mix of colors to this family, partly because there's just so many overlapping colors in this region. So typical clustering methods have a lot of trouble identifying and studying the Flora family. But we can answer the question of does the family exist with a firm, strong yes. I plotted this family in semi-major axis versus size. So this is actually all of the asteroids in the inner main belt, plotted in semi-major axis versus size. If you remember, the Massalia family showed that V in this space. So we can look, here's asteroid Flora in, it's here in the middle of what we would look for a V around the Flora family, and we do see part of a V. There's kind of a funnel cloud descending here as part of the Flora family. So it does look like there is a family connected with Flora. The other side of the V we would expect to see here, but it kind of peters out, and there's a reason for that. The reason is that there's interactions, there's resonances, interactions with the planets there that clear out asteroids on that side. So we only expect to see sort of half of the Flora family. So using the core sample method, I characterized the Flora family and found out, what its dispersion actually looks like in eccentricity and inclination. And then in semi-major axis in size, you can find that funnel cloud and measure how dispersed it is, and determine the age of the family. So I determined it to be 950 million years. Now, if you remember from the Yarkovsky effect, what it's going to do is it's going to spread out some objects that are spinning one way and some objects that are spinning the other way, two different directions. So this wing here, this funnel cloud, is likely to contain objects that are all spinning the same way, in this case prograde. So we can look at which way the objects in that group are spinning. So now I've colored prograde objects blue and retrograde objects red. And we see, yes indeed, the funnel cloud is composed primarily of blue prograde objects. So that really confirms that there is a family here. Not only that, but we can use asteroid spins to characterize or to constrain different models for the family's evolution. So this is the color code for the objects that are plotted here. And the extremely prograde ones, the ones that have spins that are 90 degrees straight up relative to their orbital plane, are plotted in dark blue. And then the objects that are extremely retrograde are plotted in dark red. And the objects that have spin axes that are in the plane, kind of between prograde and retrograde, are lighter colors. And so we can start to use this information to constrain dynamical models for the family's evolution. So what I did was I took an in-depth Spinsense survey to measure the spin sense of the objects in the Flora region to test two different dynamical models, one of which predicts that all the objects that are close to the edge of the Flora family will have very prograde spins, like very dark blue prograde spins. And the other model predicts that they will have a variety of prograde spins. They'll have 0 to 90 spins all through that range. And what I found was, this plot is a little busy, sorry about that, but the takeaway from it is that, yes, indeed, this band of prograde rotators actually shows spins that are in this whole range, some of which are very low, these white points, and then some of which are very high in the very prograde range. So I was able to test these two dynamical models for the family. So in a quick summary of the Flora family, yes, the family exists and we can define it using the techniques developed here. Find the age to be 950 million years. And then a Spinsense survey can confirm, it can test between these two different models, provides evidence for the model where the members are caught in a spin orbit resonance, and that actually changes their spin axes. So now we move to the neighboring Nysa complex. I mentioned earlier that it has 4 overlapping families. This is a very important region because it's low inclination. The inclinations here are low, and it spans a whole range of semi-major axes. So it's likely been providing a whole lot of the near-Earth objects that we want to visit, because low inclination objects are easy to get to. So 101955 Bennu is thought to come from here, the target of OSIRIS-REx. And the Japanese Hayabusa 2 mission is also going to a near-Earth asteroid that is probably from this region. But this is a confused region with a whole lot of different surface properties of different families. And in particular, you'll hear me refer to C-type, X-type, and S-type categories. C-type, these refer to the properties of their surface. C-type looks dark, carbon-like, carbonaceous or coal-like, and then S-type looks stony. So those are, the S-types are lighter and often more redder. And then X-types are kind of in between. So we'll use those terms when we look at the Nysa region. So here's the Nysa region, a zoomed in plot with the Sloan colors. And we can see there's at least this blue component and this orange component. So it helps to study those in two different components. Starting first with the redder objects, the orange objects. They form a cluster here that is a single family connected, apparently connected with 135 Hertha, which is this red square. And if you plot the objects inside this red box in semi-major axis versus eccentricity, you can see some important details about this family. And the first is that here's the Mars crossing line on the inner edge of the semi-major axis, and the Jupiter 3-to-1 resonance. And this family really spans the entire range. So it's been interacting with those resonances. And then the next thing to notice is that the family is sort of tilted. And if you fit the boundary of this family, you can find that it has a particular slope. And that particular slope is interesting because it indicates that the collision that formed this family likely had a specific property. It occurred at a specific point in the parent body's orbit, namely aphelion, which is the point where it's the furthest from the sun. Now, these ellipses here represent the distribution that you would expect to get for collisions that occur at different points in the asteroid's orbit. 180 is a collision occurring near aphelion. And the slope of this red ellipse matches the slope of the family's distribution. So we are able to say this collision likely occurred near aphelion, but also important is that there's minimal semi-major axis dispersion in this dimension. So for this family, if you recall, we want to study the age of the family from the semi-major axis dispersion. And so if we know that the actual original collision only produced a minimal amount of semi-major axis dispersion, it helps us constrain the age of the family. So we do that. I was able to find that the age of the family is 300 million years from the semi-major axis dispersion. And here's the summary for the large S-type Hertha family. There's an original collision that occurred near aphelion with minimal semi-major axis spread along that line. That gives us a Yarkovsky age estimate of 300 million years. Now, when we study the bluer objects, we're leaving the red objects behind, going to the bluer objects in the region. Right away, we can see we've removed the large Hertha family, but there's a little leftover component, which you can actually sort of start to see as a purple blob in this plot here. And that's interesting because these objects are X-types. They're right in between the C and the S-type in the color scheme. And that's important because Hertha itself is classified as an X-type. So these are likely related to object 135 Hertha. And if we take all of the objects in this region and we plot them in semi-major axis versus size, we can see that yes, they are indeed exactly near the semi-major axis of 135 Hertha, and they display this V that we've come to recognize as the Yarkovsky signature spreading out the family after its collision. And it's a narrower V. This is a narrower V than the larger one that is connected with the S-type family. So we likely have a younger family embedded within the S-type family, but different colors. So how could we get something that looks like this, two overlapping groups with different colors? Well, there are a couple of different origin scenarios. One is that they are from different parent bodies, but the parent that formed the S-type Hertha family was completely destroyed, so we don't see it anymore. Now it's very difficult to completely destroy. You have to have a particular type of collision to completely destroy the parent, but it is possible. The other scenario, which is also interesting, is that they came from the same parent body. And if they came from the same parent body, say you had a parent with a core that looked like one property and surrounding material that looked like another, and then you blew off all of this surrounding material to form the first family, and then a second collision occurred on the core to form the second family. And if that's the case, that has implications for the partial differentiation or the possible shock darkening effects of the parent body. So we can start to constrain our formation and evolution models based on the data we get here. So now moving back to those blue objects, we'll briefly talk about the Eulalia and New Polana families, which were recently distinguished in a paper by Kevin Walsh et al. 2013. So this object here, this blue object, is 142 Polana, and it's got a diffuse group of family connected with it that is likely thought to be the source of Bennu. This group of objects is much darker, much more cohesive. It's called the Eulalia family, and it's nominally connected with 495 Eulalia. But if you notice from this plot, they are very separated in eccentricity from each other. So why is Eulalia so far off? Or you can also ask the question, what's near 495 Eulalia? So now I just shifted my axes, and I'm considering the region just beyond that previous plot, and we're going to look at eccentricity and inclination. And we see there's a very, very diffuse group of objects there, indicated by that purple box, which may be connected with Eulalia. Now, the best way to tell if it's connected with Eulalia is to plot it in semi-major axis versus size and look for a V. Now, Eulalia is really close to the Jupiter 3-to-1 resonance. So half of a V exists among these purple objects. You can see this line here. But the other half of the V is missing because that resonance is right there. But this does look like it's a structure connected with Eulalia. Now, if we plot for comparison the green objects inside the green box, we see they also look like they're connected with Eulalia. And in fact, they show the same structure as the purple objects, just offset slightly in semi-major axis. So what could be happening is these could be two parts of a giant collision. I've got a little cartoon to illustrate that. If you had a giant collision on Eulalia, this dark dot, that sprayed stuff in two different directions here, also in two different directions in semi-major axis, perhaps you could maybe explain what we see, because immediately, or relatively immediately, the resonance would remove half of this component here, the purple component, which explains why it's not nearly as dense as this other group. But then over time, the Yarkovsky effect spreads out what's left, and some of the objects go this way because they have spins that make them go outward, and that just really decimates the population of Eulalias. So this family could have been it was two times as large, and this could be indicating there's two different parts to that family that we hadn't noticed. So in summary, what I just said, the family could be 2 times larger, an anisotropic collision. It sprayed things in 2 different directions. And most of the family then is gone, but we can learn from what's left. And this leaves a lot of remaining questions. We need to quantify statistically those 2 populations. Are they the same or are they different? And then do both groups spectrally look the same or do they look different? That can tell us about important connections between the family, perhaps. And then lastly, we need to ask, are these families affected by that same spin-orbit resonance that the Flora family was? Because it's likely that they could be, so we need to investigate that question. And that could have implications for the age of these 2 families. So we'll run through a quick summary of the talk in graphical format for you. So the Flora family, it exists. It's almost 1 billion years old. It's been spread out by the Yarkovsky effect. And the spin survey points toward evidence that the objects are caught in a spin-orbit resonance. The Nysa region, the Hertha family 1, shows this interesting semi-major axis versus eccentricity structure that suggests the collision happened at aphelion, which is pretty cool. And then inside that Hertha family is embedded another smaller family, which has different colors, so that has implications for a possible partial differentiation. And then the Eulalia family could possibly be two components here, one that we've missed. So that is the result there. And now future work studying the nearby families. The Vesta family, which we talked about, could possibly be 2 different families, which is important for meteorite connections and exploration of the actual surface of Vesta itself. And the Baptistina family has been blamed for the Cretaceous Palagine extinction event in the past, but We'll see if it actually pans out that way. It could also be connected, people have suggested recently it could be connected to the Flora family, which the tools that I've developed here actually really help me study that connection in detail. So that's next. And here I get to thank a lot of people for their help and support. I've been blessed with great advisors. Thank you, Rick, and my committee for meeting with me and helping me through my PhD. And the LPL grad students, can't survive grad school without them. And similarly, the admin and tech staff, who never quite seem to be noticed enough. And then the UA Graduate Christian Fellowship has really been a great support to Nathan and me and my family. And the NSF, I really could not have done this without them. And some people need pictures rather than words. My parents have taught me from day one to love God and science. And my sister, who is here, if you need any further proof that families share the same physical properties, my sister and I, and my new family, a lot of whom are here, the Dykhuises, Nathan and his parents and siblings. And then you've seen pictures of Nathan and I, and you've seen us as adults, but you probably haven't seen baby pictures, and they're cuter. So a long time ago, 5 years ago, the greatest collision in my life occurred. And as I already mentioned, we have a very dynamic family. Matthew and Jonathan, soon to be arriving. So thank you very much.
Other questions?
I have a question about the Yarkovsky effect. So do you have to assume that there is an even distribution of prograde and retrograde?
Yes and no. Collisions are not necessarily likely to produce that, and we've seen evidence of that in smaller collisions, that they don't necessarily produce that. In my particular work, I haven't been studying like the different differences between the prograde and retrograde wings of these families. In fact, now that I realize that most of my families have half of it missing because it got stuck in the resonance. But you don't have to assume that. You can sometimes test that observationally with Spinsense surveys, and there are actually ways to change the prograde and retrograde spin sense of objects, and so that's partly what we're testing when we do these surveys and when we look at the distribution in semi-major axis and size.
Chet?
Question on a similar line. I'm going back to the Eulalia family. I just had this thought: would looking at like the distribution of retrograde motions between the green family and the purple family be useful, or is that going to be, are those retrograde motions going to be randomly distributed enough where it wouldn't say much?
So there's two answers to the question. It would be great if we could test all of those spins, partly because one of the newer models has been predicting that, you know, the spins of those objects can test between different dynamical models. But those family members are very small and very dark, so our current best method for obtaining the spins is a light curve analysis, which the Flora family, which I did my survey on, is very bright, very big, and I got to use the biggest objects in that family. And those family members are a lot smaller, so it's going to be a long time before we can measure that, but it would be great if we could. I don't think I would expect it to differentiate between those two families, or to tell if they're part of the same family or not. But it might be interesting. It would be interesting for sure.
Other questions? Rob?
Really great talk. So for the Eulalia family, like half of them are missing because they're in their resonance of Jupiter. So you expect them to be just displaced from the solar system, or would you expect to find them like maybe like Trojans are around Jupiter or something like that?
So the Jupiter 3-to-1 resonance sends a lot of stuff toward Earth, so I would expect that a lot of stuff is in the near-Earth region, and then has hit the Earth in the past, and then has hit other planets, has been ejected completely. I think, so yeah, I would expect to see all of those places, especially if it's an exceptionally big family, then a lot of stuff has gotten dumped into that resonance. I think the Trojan population is more difficult to capture from the inner main belt. That would be my instinct, is that it's hard to capture things in the Jupiter-Trojan region. But I definitely think the stuff from the Eulalia family, if it was 2 times bigger, it's been everywhere.
Was there a question?
That was a great talk. Thanks, Melissa. The question I have is the difference in albedo amongst different asteroids enough to affect the shape of that V that you're fitting to the...
Yeah, for sure.
Yeah, so do you have to assume an albedo or measure an albedo before you fit that V?
Yes, albedo definitely affects it. That's a great question and great thing to think about. Albedo and then the density of the objects is actually another big one I didn't talk about. Because it's very dependent on the mass, the surface area to volume ratio of the objects. So yes, it definitely, those properties matter, and there's ways you can try to constrain them by measuring the albedo of the family members, but there are usually large uncertainties there. Density, there's huge uncertainty because we have so few, we know of 700,000 asteroids, but only a few hundred densities for asteroids. So these properties you can try to estimate, but that usually leaves large error bars. What I was able to do for the Flora family, which is actually sort of a new thing, is to compare it to a family that we have a very well-determined age. It looks very similar in properties to another family called the Karen family. And thus we can if we assume it has the same properties as that family, which is an assumption, we can actually get the age by comparison, because that family has an independent determination of the age, as well as the Yarkovsky drift. So that was the method that I employed that I didn't talk about here. But those are great questions. It's a big problem constraining those parameters.
Yeah.
Melissa, you showed the Yarkovsky spread for Flora family. Did you notice any particular feature as far as colors are concerned? Are they evenly distributed?
The floras?
Yeah.
Yes, they appear to be evenly distributed. And if I can answer, and also another interesting question too, sometimes you say, well, your method might assume that all the families are the same color and all the objects are the same color, and you might miss information like 2 different families. Well, actually, we don't assume that. We look for different color families that are overlapping. And in the Flora's case, some people have said, well, maybe it's a mix of colors. But we actually don't see that V to be composed of anything except S-type ordinary chondritic-like material. There's no residual remnants of any other different color, really, in the floras. They seem to be an even distribution, albeit with scatter.
Any other questions?
How would you tell the difference between 2 families that had the same color that were really close together? Or is that possible?
That is impossible for me and for almost everyone. Yeah, but it is, so you can ask, if they have the same age, the same dynamical properties, and the same color, well, they would be the same family almost, If they were from the same collision, then they would be the same family. But so that age is different. We have examples where we have 2 families, one of which is much younger inside. Well, it actually impacted onto a member of a previous family. So we have a big V, and then we have a teeny v. And those cases, you say, okay, well, there's 2 different age events happening here. There have to be. And that's one of the things, the Vesta family that I was talking about, which is really interesting, a lot of connections. There might be 2 families there, but it's really hard to tell, because you're right. They look the same, and they're in the same dynamical space. But they do maybe show 2 different V's. Might be how we can do it.
Okay, well, thank you very much, Melissa. Thanks, everyone. And now I'll have to ask everyone to leave.
Aw.